Trying to work a financial problem here. This is a compound interest problem. The first three parts of the problem I've grouped together because they're going to be based off of the same formula. The last part, part D, uses a slightly different formula. And so the first three is going to use our standard compound interest formula, which is the future value of the loan. That's going to be the principal times 1 plus my rate divided by the number of compounding periods raised to the number of compounding periods times my time in years. And so n is the number of compounding periods per year. So n is the number of compounding periods per year. R is my interest rate. And remember, that's a ratio, not a percentage when we put it into the formula. And then T is time in years, unless I tell you otherwise, or unless the book tells you otherwise. P, that's the principal or the value of the loan. So principal value of loan. Okay, so with that put together, my principal, so let's do part A over here. My principal equals 10,000, and that's going to be the same for all of these. My rate is going to be, instead of 1.55%, I'm going to move that decimal place over twice. I'm going to divide by 100 and say this is 0.0155, because that's the actual number I'll use in the formula. And then the only thing that's actually going to change in working this problem is the number of compounding periods, because my T is 5 years. And so that's actually, I really should kind of move A down here, because that is constant for all of these parts, or for all of these problems. The only thing that's going to change when I'm working this problem is the number of compounding periods. And so semi-annually, that means twice per year, right? So n equals 2. And then quarterly, that's going to tell me 4 times a year. So that'll be n equals 4. And then compounded monthly, well, 12 months in a year, right? So n equals 12 for monthly. Compounded continuously is a slightly different animal. We will take a look at that differently on a different page at the end. It takes a different formula, a different model. Okay, so if I want to do A, that's going to be my future value of the loan at the end of the 5 years will be A equals 10,000 times 1 plus my rate, 0.155. I'm sorry, 0.0155. Very important 0 there. Divided by, and this is what will change between the problems. So in this problem, it's 2 raised to the 2 times 5. And if I take that and I punch it into my lovely calculator, what am I going to get? I'm going to get 10,000 times 1 plus 0.0155 divided by 2 raised to the, make sure that both of the numbers, the 2 times the 5, ends up in the exponent. And I end up with a future value of, does that number make sense? Yeah, that seems reasonable. $10,802. And we'll round to the penny just because we're penny pinchers, so to the 59 cents. And so that's the answer for A. The only difference between A and B is that in B, we're compounding quarterly. And so that future value is going to look really similar. It's going to be 10,000. It'll be 1 plus, and then the 0.0. I keep wanting to leave that 0 off, but it's very important. Divide that by 4 instead of 2 this time, to the 4 times 5. And I'm just going to go back, and I'm actually just going to edit this in my calculator because I'm only changing that 2 to a 4. And I'm only changing that 2 to a 4. I'm going to press enter. And a little bit of an expectation, a little bit of a guess as to what will happen as I have more compounding periods is a good idea, because it gives me an intuition as to whether or not I'm right when I change these things. And the more compounding periods, the more interest has been converted to principal, the more interest I'm earning. So I would expect this number to be slightly higher. And it is slightly higher. This one is going to be 10,804.2. So 20 cents. It's a 20, not a whatever ugly thing I just wrote was. All right, so that's my B. And then my C, same old, except this time instead of compounding semi-annually or quarterly, we're compounding monthly, so n equals 12. And so I have A equals 10,000. 1 plus 0.0155, all divided by 12, give me a monthly interest rate, and my number of periods up here. So 12 times 5 will give me 60 periods up there. All right, now let's type that into the calculator. And again, all I'm really doing is changing that 4 to a 12 from my previous calculation. Type that in, and again, I'm going to get marginally more, a little bit more, because a little bit more interest has been converted to principal that's now earning more interest. I have $10,805.28. Now, the last part of the question says, what if, rather than twice a year or 4 times a year or 12 times a year, what if every instant of every day, any interest that gets earned gets instantly converted into principal and starts earning more interest? And that requires a different formula. That requires a different model. And that model is the future value equals, and it's going to be principal times the number E raised to the rate times time. And so this E is a constant number, just as pi is a constant number. It's an irrational number. It's very important in the world of exponential modeling. It's kind of pi's cousin as far as its importance and its usefulness in the world of mathematics. And this is one of the big ways that it's used in modeling, is for this kind of, it's called exponential growth, because things are growing with the exponential. We've got our variables in the exponent. And so there's an acceleration to the growth that you can see, especially if you graph this out. But practically, my P, my R, and my T, they mean the same thing. I just don't have an N anymore because I'm not compounding it a certain number of times. I'm compounding it continuously. And so let's put these numbers in. So I've got 10,000, and then E is a number. 2.7 something, and just there's an E button on your calculator, and I'll show it to you if you can't find it. But there's an E button on your calculator. Use that to then put my rate, which is the 0.0155 times my time, which is my 5 years. I go to my calculator. I type all that in, 10,000, and times. And it's often you have to hit the second button and then the LN key because it's a cousin to, it's an inverse function for the natural log. Don't need that. That's just why it's there. That's the relationship. Okay, and so now 0.0155 times 5. And what am I expecting? I'm expecting another marginal growth because I've already compounded it 12 times. And so I'm really not compounding it that many more times if you think about it relative to what I've already done. So I don't expect a huge change here. I expect another marginal increase. And that's exactly what we're getting. So I get 10,805 and then 0.82. And so that's my continuously compounding, and those are my semi-annually, quarterly, and monthly compounding. All right, I hope this helps out. Let me know if we have any more questions.